section 2, that is about measurements in experiment, right? Let's dive in with this lesson. Firstly, that I want to explain it for you. First thing that I want to explain for you is dimension. What's dimension? Let's read the definition of dimension. It says a measure of a specific physical quantity. This is the first simple definition, a measure of a specific physical quantity, or the description of what kind of physical quantity is represented by a certain measurement. So it's a description of what? Description of a physical quantity is a measure of physical quantity. This measurement is called dimension. Let me give you an example. For example, about this room, about any room. Think about the dimensions, let's say, within the room. How many dimensions are there, let's say, within the room? We have 3 dimensions. We have length, width, and height, right? That's why by means of these dimensions, we can describe the room, which is a 3D object. Let me give you other examples for, let's say, elaborating the subject and understanding the subject. Let me explain dimension for you. I want to give you some example about dimension. For example, think about this point. How many dimensions are there in this? Let me correct it here. How many dimensions are there in this point? Yeah, think about it. What do you say about this line? What do you say about this rectangle? What do you say about, for example, this object? This, let's say, 3D object, right? This is cube, actually. This is 0 dimension. Point has no dimension. That's why it's 0 dimension. This one, the line has only 1 dimension, and it's 1D. This one has length and width. That's why it's 2-dimensional object. And this one, the cube, or any, for example, the room, any cube, any box actually has 3 dimensions. What does it mean? It means it has length, width, and let's say height. That's why 3D object. This is about the dimension in general, right? Let's move on to another thing. And I told you a dimension is a description of physical quantity. But physical quantities in general are of 2 types. Either we have fundamental quantities or we have derived quantities. Fundamental quantities like what? Fundamental quantities like mass, for example, time, length, they are fundamental or base quantities. Why do we say they are fundamental or base quantities? Because they are original. They're original quantities. It means they don't depend on other, let's say, quantities, right? We have 7 fundamental quantities now in our textbook. Let's say read them one by one. We have a let's say table for these dimensions, right? So fundamental physical quantities, we have a, for example, graph here, diagram, physical quantities of 2 types, fundamental quantities and derived quantities. I told you fundamental quantities, the quantity that which does not depend on, it doesn't depend on any other physical quantity. They are independent, yeah? They are independent, or we can say base quantities. Like what? Like, for example, mass, time, and etc. Let's read the 7 fundamental quantities one by one. The first one, actually, we have a table here. We have some columns. The first column talks about fundamental quantity. The second column, the symbol of fundamental quantity. Actually, this symbol and unit, let's say, are used in SI. Let me tell you a summary about the SI. SI is abbreviation of System International of Units. In 1960, actually, scientists all over the world held a conference about the dimensions or units in general in physics, especially about the physics. I'm talking about the physics. And they agreed on some standards for fundamental quantities, for derived quantities. That's why this system is called System International of Units, or SI unit. Actually, I told you, scientists agreed on some standards for time, for example, for mass, for any other quantities, right? So right now, uh, these symbols are used in SI unit name, and they are, let's say, international symbols, and let's say uh, they are international symbols, right? For example, for length, we cannot use. Sometimes we use, let's say, delta x for length. We use L, but we cannot use, for example, T for length. T is dedicated for time, right? Let's read them one by one. The first fundamental quantity is length. Symbol of length is L small. Unit name meter. Unit symbol M small. And the definition of, let's say, length based on SI is what? The distance traveled by light in a vacuum. The distance that is traveled by in a vacuum is a distance, as a definition for length. About mass, the second fundamental quantity is mass. The symbol of mass is M. Mass, let's say, is measured in kilogram. So kilogram is the unit of mass. Mass is a dimension or quantity. Unit, a kilogram is a unit, right? And the symbol of kilogram is kg. Definition of kilogram is the mass of a typical kilogram. Yeah, mass of a typical kilogram. Time, the third fundamental quantity. Symbol T small. Unit, let's say, symbol second. This unit name second, and symbol is S small. Definition of, let's say, second is a particular period of a radio wave emitted from cesium-133 atom. Particular period of radio wave emitted by cesium-133. It's an element, it's a metal, right? After that, we have temperature. Symbol of temperature is T small, T capital, excuse me. T small for time. You see? So you have to differentiate between these, let's say, units. You have to be accurate. You cannot use T small for temperature. That's why T small is dedicated only for time. T capital is dedicated for temperature, right? The unit of temperature is Kelvin. Sometimes we use Celsius in SI, but this is scientific unit, especially Kelvin is scientific unit for temperature. Unit symbol is K capital. And here we have the definition of, let's say, a temperature, 1/273 of the triple point of water. This is the definition of, let's say, temperature. Amount of matter, the symbol of amount of matter is M, N small, excuse me, N small. M for mass, actually. M for mass, N small for amount of matter. The unit of amount of matter is mole. Unit symbol is MOL. And the definition of unit amount of matter, the amount of matter in 0.012 kilogram of carbon 12. 0.012, we can say 12 grams of carbon 12. Electric current. Electric current, the symbol of electric current is I capital. It's measured in ampere, right? Ampere. The unit symbol is A capital. And the definition of ampere is definition of electric current is the current which runs into parallel, let's say, wires that are away from one another by 1 meters, right? The current which runs into parallel wires placed on 1 meter apart and gives rise to a force, let's say, per unit length of each wire. This is the definition of electric current. Luminous intensity. Luminous intensity, especially we use it for light bulbs. luminous intensity is dedicated for light actually. The symbol of luminous intensity is IV, I sub V. The unit is candela, CD. And the definition of luminous intensity is the intensity in a given direction of a source of monochromatic light. Monochromatic light like this, for example. This laser beam is monochromatic. Let me show it to you. This is a laser beam and monochromatic, right? Monochromatic. Actually, we use the scientists agreed on, for example, using green, let's say light for this purpose. Intensity in a given direction of a monochromatic light. I told you, single color light. It's not visible. Actually, it's not white light. It's a part of visible light, actually. It's a part of white light. One wavelength, one color, single color means monochromatic means single color. Simply, we can say. So green, especially green, which is equal to 1 over 683 watt, right? For each steradian unit of a solid angle. Steradian means the unit of solid angle. Actually, these are fundamental units, right? So we have 7 fundamental units versus a lot of derived quantities. We have 7 fundamental quantities in physics versus what? Versus a lot of derived quantities. And these, why do we say derived quantities? Because they are driven from fundamental quantities. For example, think about velocity. Velocity is not fundamental, is derived quantity. Why? Because velocity, let's say, is derived from what? From distance over time, from length over time. That's why it's not fundamental. Velocity is a derived quantity, right? But here in your textbook, let's say we have 7 derived quantities. Let's read them one by one. Let me read the definition for you. Actually, derived quantity is the quantity that depends on what? That depends on fundamental quantities, right? A quantity that depends on fundamental quantities such as acceleration, force, velocity, and energy. They are derived quantities. Let's read the symbol and the unit of these quantities in SI. I told you they are valid in SI. The first derived quantity is area. The symbol of area is a capital. Unit symbol, or unit name, meter square. Unit symbol, square meter. Derivation. Actually, derivation means the rule. Derivation. Where does it come from? Length, time, width. Whenever you multiply length, time, width, you get the, for example, area like this. This length, and this is width. Whenever you multiply them together, you find the area. Volume, and another derived quantity is volume. Symbol of volume, V capital. Be aware, V capital for volume, V small for velocity. You have to, let's say, distinguish between these symbols, actually. Don't confuse the units together, right? About the unit of volume, we have cubic meter, right? This is the symbol, and derivation of volume is, it comes from what? It comes from length time width times height, like this. Like this cube, for example, it has a volume. So any 3D object has a volume. And actually, volume is not dedicated only for, let's say, 3D objects. And in general, no problem. I say 3D object because we have 3 dimensions, right? Let's move on to another one, density. Density, the unit of density is, the symbol of density is rho. This is rho. We can, this is called rho actually. we can use, for example, d capital for density, no problem. I write it for you. This is rho, right? The unit of density is kilogram per cubic meter, kilogram per cubic meter. And the derivation of density is mass over volume, mass over volume. Let's move on to another one. Velocity is another physical drive physical quantity, velocity, v small. The unit of velocity meter per second. And the rule is distance over time. We have acceleration, symbol of a small, symbol of acceleration is a small. The unit of meter per second square. Velocity over time is a derivation of, let's say, acceleration. You see, let's say here, all of these physical quantities are driven from what? They are driven from fundamental quantities. You see, length, for example, times width. Two, let's say, length times width, or let's move on to other, mass over volume. Mass is fundamental quantity. Volume, of course, is another, let's say, quantity. So any derived quantity is not original, is driven from what? Any derived quantity is driven from other, let's say, quantities. Distance over time, for example, velocity comes from distance over time. Distance is a quantity and time is another quantity. That's why whenever you divide them together, you can find the velocity, which is not fundamental, it's derived quantity, right? Let's move on to the force. This symbol is F capital. The unit of force is Newton. This symbol of Newton is N capital. And Newton comes from mass times acceleration. This is a derivation. And energy, the last one that is mentioned in our textbook of energy, E capital is the symbol of energy. The unit of energy is joule, J capital, and the derivation is force times distance, right? Let's move on to another, let's say, other subject. We have some prefixes for prefixes. We have this table. Prefixes or for powers of 10 within metric units. Actually, what is prefix? Prefix is a, let's say, is a using of some symbols in front of the, for example, in front of the unit in order to simplify our speech. In order to simplify. Let me give you an example of prefix. For example, the distance between, for example, two neighboring atoms in a solid is this. Let me write it for you. The distance between, for example, two neighboring atoms is in a solid. I want you to read it for me, right? I want you to read this number for me, or but right now I wanna, let's say, I wanna keep going the explanation. After that, I, let's say, give you some other example, right? And in this table, actually, we have tera, giga, mega, kilo, deca, centi, milli, micro, nano, and femto, right? Here in this table, actually, only the prefixes that are let's say, measured, only the prefixes that are marked in bold is, let's say, required for a student. A student is not required, for example, to know about the tera, to memorize giga, for example, right? That's why you focus only on the bold ones, For example, focus on mega, focus on kilo, centi, milli, micro, and that's it. We have only, I think we have five, 1, 2, 3, 4, 5, let's say, 5 prefixes that are used in especially let's say, in our textbook. And I told you prefix is a kind of simplification actually for our speech, right? Uh, if I want to, for example, write, if I, let's say, go to the, for example, grocery store, and I want to buy, for example, uh, I want to buy tomato, for example. I don't say, give me 1,000 grams of tomato. I say, give me 1 kilogram of tomato. Kilogram, right? So I use kilo. Unconsciously, this person actually simplifies his or her speech by using prefixes. So the usage of prefix in our daily life actually is for simplicity, right? I say kilogram. I don't say, for example, 1,000 grams, right? And we have a lot of examples actually. Uh, let's let me read the table. After that, I'll give you some examples about the prefixes, right? Terra, actually, it's not required for a student, but it's beneficial. No problem. Let's read them together. Prefix, the name of prefix is Terra, symbol of T capital, right? Power is 10 to the power 12, 10 to the power 12. Value is, we have 1 followed by 12 zeros, right? Giga, we have giga here, symbol of giga, G capital, power of giga 10 to the power 9. How many zeros let's say, are there in giga, in 1 giga? 9 zeros, means 1 followed by 9 zeros. Mega, M capital, is the symbol of mega, right? Power 10 to the power 6. And the value of mega means million, yeah, million. 1 followed by 6 zeros. Let's move on to kilo, K capital, symbol of, let's say, power of kilo, 10 to the power 3. Value of kilo, 1,000, means 1 followed by 3 zeros. Here we have some examples, for example, about the mega. Mega is included for our explanation. Mega is actually, you have to know about the mega and kilo. I told you centi, milli, and micro. Only 5 of these table are, like, let's say, required for students. 1 megameter means 10 to the power 6 meters, right? So by using prefix, you can simplify our speech and others understand you. About the, for example, kilometers, 1 kilometer is equal to 10 to the power 3 meters, right? We have, for example, 10 to the power 0 is equal to 1. It doesn't mention any, it doesn't have any name here. About the deca, the symbol dA, 10 to the power 1, the value is 10, right? Centi, focus on centi and kilo, milli, mega. We have 5 important, 5 bold ones. You see, they are, let's say, marked in bold. That's why the students have to memorize these, let's say, units, these prefixes. Centi, symbol of centi, C small. Let's say this is the power of centi, 10 to the power negative 2. And this is the value, 100ths. You can say, let's say 100ths, right? Or 1 over 100. 1 centimeter is equal to 10 to the power negative 2 meters. I want you to memorize these powers. Milli, we have milli. The symbol of milli, M small. Power of milli, 10 to the power negative 3. 1 over 1,000, or we can say 1,000th. 1,000, yeah. 1 millimeters, 10 to the power negative 3 meters. Micro, the symbol of micro is mu. This is called mu, but we read it, let's say, micro. The power of micro 10 to the power negative 6. 1 over million or 1 millionth. You can say 1 millionth or 1 over million. 1 micrometer is equal to 10 to the power negative 6 meters. And others are not required, but let's read them together. Nano, the symbol of nano is in small. Power of nano 10 to the power negative 9. And the value of nano, 1, let's say, billionth or 1 over 1 billion, right? Femto, f small, 10 to the power negative 15, 1 over, let's say, trillionth. You can say 1 trillionth or 1 over trillion. Actually, it's not required for you, no problem. Leave them.